Okay guys, so we talked about how we can approximate a differential equation using Euler's method, right, which is essentially using the first two terms of the Taylor series of our solution, right? And we looked at if we picked h equal to 0.5, then we had a solution that was an approximation that wasn't really that great, and then when we use h equals 0.2, we got a better solution. So the question is, what's a good optimum value for our step size h? So that's what we're going to talk about now. So what is a good value for the step size h? Of Euler's method. Now there's a lot of derivation that we could do here, but we're not going to go into all of that. We're just going to put it down. And here we're going to say choose h to be no smaller than h equal to the square root of 2 times delta over m, where m is going to be a bound for our second derivative of our solution. Okay, so m is going to essentially be the largest value that our second derivative can get on the interval. Let's say a to b. And we'll just pick delta b equal to negative 10 to the negative 15. Although it doesn't have to be, it could be any value you want it to be determined depending on the precision of your computer, right? So this is kind of the precision of your computer numbers, okay? Anything smaller than this value h will introduce round off error, and we want to avoid that. So we want our h to be no smaller than this. Anything smaller than this will introduce round off error. So let's look at an example. Like I said before, the delta in this case is, our delta in this case is going to just depend on the computer, how the computer stores numbers and the precision of the computer. All right, so very good. Let's do an example. What is the minimum value of h for, here we have y prime equals y minus t squared plus 1, y of 0 is equal to 0.5, okay, on our interval 0 to 2, okay, on our interval from 0 to 2. So if we look at that, okay, it's not too hairy, it's not too difficult. The first thing we have to know is that for me to be able to figure out what the value of h is, I have to know something about the second derivative of y, right? I need to know how big the second derivative of y could possibly be. That could be a difficult proposition to know what the bound for the second derivative of y would have to be. And that could take some more math that you guys might not know. But there's something that we can do to be able to figure out what this will be, is we already know what the solution of y is, right? We already know what the solution y is equal to. Y of t, we already have seen. So the solution of the differential equation is, we saw it was y of t is equal to, I believe it was t squared plus 2t minus 1 minus, or what is it? I think t squared plus 2t minus 1 minus 0.5 e to the t, I believe. I believe this is what we got the last time. Or was it t squared minus 2t plus 1? This is that. Okay. And so this is what we got last time when we solved this. And I can find the second derivative of this. So y prime of t is equal to 2t minus 2 minus 0.5 e to the t. And then the second derivative is going to be 2 minus 0.5 e to the t. Okay. And on the interval, from 0 to 2, the absolute value of y prime of t, the biggest that this guy is going to be equal to, I think, when is that going to be the maximum value? I believe it's when t is going to be equal to 2. That's when this is going to be as large as it can. No, what's the maximum value on the interval from 0 to 2? I think 2 is going to be the maximum value. This is the largest value. We can always use a graph or a calculator to be able to find that for sure, but I think 2 is probably the maximum value of this particular function. Okay, so that's going to be my m. And so I can say, okay, since I know that, I can say that h is equal to the square root of 2 times, what is that going to be? Delta over 2. And my delta in this case is 10 to the negative 15. So actually, let me just write that. So get square root of 10 to the negative 15. Square root of 10 to the negative 15 is, what is that? 10 to the negative 7 halves, right? Negative 15 halves. 15 halves is negative 7.5. I think that's what I meant to say. Yeah. And whatever that may be. So that's going to be our h in this particular case. Okay. So we don't want to make our value of h any smaller than that. Anything smaller than that will introduce round off error. So all this method is, that is a really small value of h, right? That if we that we have here. But all this method is great and all, but it'd be better if we had something else that we can use instead. So that's what we want to talk about now. What's a different method that we can use? And I need to bring back my bears. I think my bears are very helpful. I don't have my bears here today. I should have brought my bears here. Anyway, so let's talk about a different method. So we have all this method. I want to talk about a different method of approximating a differential equation. That's going to be Taylor's method. That's what we're going to talk about next. So let's erase this. And just what you would think would happen, right, for Taylor's method, instead of using just 2 terms of the Taylor series, we're going to use as many terms of the Taylor series as I like. I might use 3 terms, 4 terms, 5 terms, 6 terms, etc. of the Taylor series. And that will give me different Taylor methods. So that's what we want to do now. We want to extend this idea of Euler's method to any number of terms of our Taylor series that we're going to use for approximation. Okay. So Taylor's method. Of order k. Taylor method of order k. And this is what it looks like. We have y sub n plus 1 is equal to y sub n plus t sub k of t sub n, y sub n. And then we have y sub 0 is equal to, let's say, alpha, so some value that this is equal to. So we have y sub n plus 1 is equal to y sub n plus t sub k t sub n, y sub n. Y sub 0 is equal to alpha. Okay. And I actually, when I do this, I actually, and so what is t sub k? Let's talk about what t sub k is. Where t sub k, t sub n, y sub n, I'm getting ahead of myself, is going to be equal to, remember those terms of the Taylor series that we didn't include, right? The next term of the Taylor series, if we were to think about this as a Taylor series, we have y sub n plus y sub n prime times h, okay, plus y sub n double prime times h squared over 2 factorial, right? Plus y sub n triple prime, h cubed over 3 factorial, plus all the way up to whatever our value of k that we're trying to use here. So it's going to be, I'll say y sub n, the kth derivative of y sub n, h to the k over k factorial. And really what this is, when you think about it, these are just the terms of the Taylor series, right? So if I had just stopped with this term, then this would just be Euler's method, right? If I add another term, then I have Taylor series of order 2. Add another term, I have Taylor series of order 3, all the way up to order k. Okay, so order 1 is Euler's method. So Euler's method, let's say, is the Taylor method. The method of order 1, or first order, okay, of order 1. Because essentially what we do is we start with the first derivative. That would be Taylor's method of order 1. So let's find, let's put down here, let's find the Taylor methods of order 2 and 4 for y prime equal to, what do we have? Y minus t squared plus 1. Y of 0 is equal to 0.5. Okay, find the Taylor methods Taylor methods of order 2 and 4 for y prime equal to y minus t squared plus 1. Y of 0 is equal to 0.5. Okay. So let's do that. To be able to find those Taylor methods, right, we need to find the first derivative, which we already have, of y. We need to find the second derivative of y. We need to find the third derivative of y, and we need to find the fourth derivative of y, right? Because we want to get up to the fourth Taylor method. So let's do that. We know that y prime, let's put it down here, y prime is equal to y minus t squared plus 1. Okay, so y prime we know is equal to, so I'm going to say we know that y prime is equal to y minus t squared plus 1. How do I find y double prime? Well, I need to take the derivative with respect to t. So when I take the derivative with respect to t, again, of this particular one, so I'll say y double prime, that's equal to y minus t squared plus 1 prime. Okay. And I'm going to take the derivative with respect to t. What is the derivative of y with respect to t? Well, it's going to be y prime. What's the derivative of t squared with respect to t? It's going to be minus 2t. Okay. Derivative of 1 with respect to t is 0. When I plug in, but what is y prime? Well, y prime is equal to, what did we say it was? Y prime is equal to y minus t squared plus 1. So I get y minus t squared plus 1, and then I get a minus 2t. So this is what we get when we find y double prime. We get y minus t squared plus 1 minus 2t. Okay. Well, now we need to find y triple prime. Well, what's y triple prime? Well, it's going to be y double prime, the derivative of y double prime. What's the derivative of y double prime? Well, let's find out what that is. So it's going to be y, I'm going to put this in order, minus t squared minus 2t plus 1 prime. Right, this is what this is. Take the derivative of this, we end up with y prime minus 2t minus 2, right? And then, but what is y prime? Well, we already know that y prime is going to be y minus t squared plus 1. And then we get a minus 2t minus 2. So far, so good, right? And what's our fourth derivative of y? Fourth derivative of y. Okay. Let's plug that in. Fourth derivative of y, well, we need to take the derivative of the derivative of the third derivative, if I can talk. Okay, derivative of the third derivative. So we get y minus t squared minus 2t. When I add these guys together, plus 1 minus 2, that is a minus 1. Oh, it's the same thing. Is it the same thing? Plus 1 minus 1. Close, similar, right? If I didn't make a mistake. Let's see, minus 2t. Let's look at 1 minus t squared plus 2t plus 1. We'll take the derivative of that, get minus 2t minus 2. That looks fine. And then when we plug in our derivative, yeah, so when I take the derivative of this, I get y prime minus 2t minus 2. And when I plug that in, I get the same thing I got up here, right? This is going to be y minus t squared minus 2t minus 1. Okay. So that is our first, second, third, and fourth derivative. Okay. And so what would those Taylor methods of order 2 and 4 look like? Let's put down a Taylor method of order 2. Order 2. Okay. See here, that would be y sub n plus 1 equals, right, y sub n. And we just go to the second derivative, right? We go to the second derivative. So we'll do plus, we have y sub n plus y sub n prime. Y sub n prime, we know that to be y sub n minus t sub n squared plus 1, that times h. Okay, that's going to be my y prime, y sub n prime, which is what we want. Then we want the second derivative, y sub n double prime, plus, we have, in brackets again, y sub n minus t sub n squared. I'm looking for it. Like I can see it. Can you see it? Yes, I can see it now. Minus 2t sub n plus 1. Okay. And then that'd be times h squared. All that divided by 2. And then we have our initial condition, y sub 0 is equal to 0.5, I believe is what we have. So that's the Taylor method of order 2. Okay. So not too bad, not too shabby, right? Let's do Taylor method of order 4. Do we have enough space to put it? So that's a good question. Let's put it over here. I'm going to have to erase this. With Taylor method of order 4, I need to go up to the fourth derivative. I think this is enough space for me to put it. I'm going to have to do multiple lines. Okay, so Taylor method of order 4. So we have y sub n plus 1, okay, equals y sub n plus. Now I need to go up to the fourth derivative, right? So essentially I tack on these two guys that I've already done. Y sub n minus t sub n squared plus 1 times h plus, I'm going to need more space. I'll just make it another line. Plus, what do we have for our next line? Y sub n minus t sub n squared minus 2 t sub n plus 1 h over 2 plus. Now let's go to the third derivative, which will be y sub n, going to the third derivative, minus t sub n squared minus 2 t sub n plus minus 1 this time, h squared over 3 factorial, right? This is 2 factorial, plus, and then our last one is going to be y sub n minus t sub n squared minus 2 t sub n minus 1 h to the third. Oh, that's going to be the fourth derivative, right? But it's going to be 3. That's not fourth derivative, but no, this is, so we have, this is going to be, what do we have? I'm looking at it. First derivative, second derivative, third derivative. This is the fourth derivative. Oh, you guys probably know that. This should be squared, this should be cubed. All right, that's what I was looking for. H to the fourth over 4 factorial. There we go. And then our last one is going to be y sub 0 is equal to 0.5. Oh my goodness. And this is our Taylor method of order 4, right? On a test, I don't think I'm going to give you guys a